Hello and welcome to Lesson 9 of 20 in the Ursa Campus Breakdown course on Introductory Statistics and Probability. This is Module 2, Probability, Part 3, Fundamentals of Probability. Let's get started. In this lesson, we'll take a look at the key concepts related to probability, which are important when it comes to looking at uncertainty in general. We'll look at the following topics: experiments and outcomes, sample spaces and random variables, definition of probability, general rules for probability, experiments with equally likely outcomes, independent versus dependent events, and we'll take a look at how to use the counting principles that we looked at previously in this module and apply them towards calculating probabilities. An experiment is defined as an activity or situation where the possible outcomes can be observed or measured. Now there's myriad examples of experiments. Here's just a few. Flipping a two-sided coin once, rolling two six-sided dice, or recording lightning strikes during a 24-hour period. Now obviously the list is quite diverse and does suggest that the number of possible experiments that one could conceive of is limited really only by one's imagination. Now, in each of the experiments mentioned above, there is more than one possible outcome. So that's something that they all have in common. And therefore, these can be thought of as activities or situations that are inherently uncertain. In fact, there would be no point in having an experiment that wasn't uncertain because there would be no need to do it, unless you were just doing it for enjoyment's sake. An outcome is a possible result of an experiment. So in example 1, we take a look at these experiments that were mentioned in the previous slide. So one possible outcome for a single coin toss would be heads, which we could denote with the letter H. And one possible result from rolling two dice is the combination of getting a 2 on one die and a 5 on the other, which we can write as bracket 2 comma 5 close bracket. And if we're measuring the number of lightning strikes in 24 hours, one possible outcome could be that there are 4 such strikes. The sample space for an experiment is the set of all possible outcomes. In example 2, we take a look at those same experiments we were discussing previously, and now we can list all of the possible outcomes. So for a single coin toss, there are 2 possible outcomes, and that is the set heads or tails. If we roll 2 dice, there are actually 36 possible outcomes because there are 6 possible outcomes for each die, and if we use the multiplication principle, it's no surprise that we get 6 to the power 2, or 6 times 6 equals 36. And you can see the list showing on the slide gives an idea of what that list of outcomes would look like. We can systematically list them starting from the lowest outcome of 1, 1, and then 1, 2, and then 1, 3, and then dot, 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 and then you see some more. There's 2 and 1, or 2 and 2. We can even write dot, dot, dot again. It's another way of writing this list without writing every single possible outcome. And then finally, the last outcome, if we listed them in this sort of order, would be the highest possible outcome, which is to get 6 on both dice. And then for the number of lightning strikes in 24 hours, the possible values could be from a minimum of 0 through 1, 2, 3, etc. And in this particular case, theoretically, there would be no upper bound, so we would just end it with a dot, dot, dot. This is an infinite. This particular sample space is infinite on the upper end. The sample space is analogous to the universal set U that we discussed previously in this module. It is written with the symbol S, and the number of elements in the sample space S is written as NS. So in example 3, we would say that for a single coin toss, the sample space equals the set heads and tails, and the number of elements in the sample space is 2. And for 2 dice rolled, you can see the list then again listed there, and the number of elements would be the 36 that we talked about before. In the case of the number of lightning strikes in 24 hours, the sample space would be the numbers from 0 on upwards, and because it is unbounded on the upper end, we actually have a number of elements in the sample space here equaling infinity. An event is a subset of an experiment sample space. So in example 4, if we look at an experiment where 2 dice are rolled, we could define, well, there's many different events that we could define, but here's 2 that we could define based on that experiment. We could define event A as the event that both dice show the same number. So that would be the set that includes 1, 1 and 2, 2 and so on until 6, 6. We can also define another event B, which is the event that the sum of the 2 dice is 11. And that would be the set of outcomes 5 and 6 and 6 and 5. And then we could state the number of elements in these defined events. The number of elements in A would be 6, and the number of elements in B would be 2. If an event is defined such that it includes all of the possible outcomes of the experiment, then the event is equal to the sample space for that experiment. So in example 5, if we define C as the event that the sum of 2 rolled dice is less than 13, then essentially, since you can never get, actually, in fact, you can never get more than 12 when you roll 2 dice. So that would imply that all of the possible sums that you could get would be less than 13. So the set C is actually equal to the sample space here. And so NC will equal NS, which equals 36. Now, such events are said to be certain events because the event C, if the experiment is that we roll 2 dice, then we are certain that the sum will be less than 13. There's actually no uncertainty there. At the other extreme, if an event is defined such that it includes none of the possible outcomes of the experiment, then the event is equal to the empty set. So in example 6, if we define C as the event that one of the 2 dice is showing the number 7, since we know that each die only goes from 1 through 6, that would actually be impossible. So in this case, the event C is just the empty set. And so the number of elements in C, of course, would equal 0. And such events are said to be impossible events because they can't actually occur. If an event contains any but not all of the possible outcomes in the experiment's sample space, then it is neither certain nor impossible, but rather we call this an uncertain event. And of course, statistics is primarily focused on uncertain events, because when an event is uncertain, we don't know for sure whether or not it's going to happen or not, and we may try to employ statistical methods to predict the likelihood that it may or may not happen. In example 7, a coin is tossed 3 times in succession, and the side showing is recorded for each toss. For each of the following events, list the outcomes comprising the event and the number of elements in the event. So in part A, the event is actually S, the sample space for the experiment. In part B, we have A equals the event that the first coin is heads. In C, we have event B, which is the event that there are 3 tails. And in part D, we have C, which is the event that there are an equal number of heads and tails. So the answer is are as follows. The sample space we can see here, and we've actually looked at this previously as the situation of flipping a coin 3 times, and we can see that we have all the possibilities of getting heads or tails, and of course the number of elements equals 8 because we have 2 possible outcomes each time to the power of 3, which is the number of times we're tossing the coin, so we get ns equals 8. Now in part B, the event is that the first coin is heads. Now clearly this is going to be a smaller set of outcomes because the first coin being H will not equal to the entire sample space clearly because the first coin could also be tails. So we end up, you can see here the list, we have heads, 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 tails, heads, tail, heads, and heads, tails, tails. And the number of elements in set A is equal to 4. Which shouldn't surprise that that's exactly half of the size of the sample space because there's 2 possibilities for that first coin, and only one of them is that it's heads. So 1 out of 2 is a half. So shouldn't be surprising here that the number of elements in set A is exactly 1/2 of the number of elements in the sample space. Now, in part C, we're looking at the set B, which is the event that there are 3 tails. Now, that could only happen one way, and that's getting tails, tails, and tails, because there's only 3 tosses. So therefore, the number of elements is just equal to 1, because there's only one way that that can happen. And finally, in part D, C is the event that there is an equal number of heads and tails. Well, it turns out that the answer to this, that C is the answer is that C is the empty set, because the total number of coin tosses is 3, and since there can only be heads or tails each time, there would need to be an even number of tosses in order for them to be split equally between heads and tails. So since 3 is an odd number, it's impossible to get the same number of heads or tails. There has to be more heads or more tails. So the number of elements in C is 0. A random variable is something in particular about an experiment that we are interested in observing or measuring, whose outcome is uncertain. For any single experiment, we can define a number of different possible random variables, and in many ways this is really, again, just limited to our imagination. So in example 8, if a 2-sided coin is tossed once, we can describe a random variable x equals the side showing. So when a random variable is defined in this way, the next step is to indicate the possible values that the random variable can take on. So if x is the side showing, then we would say that x equals, and then we would list the values. Here it would be x equals heads or tails, and we just use the comma to separate those two. In other words, we're saying here that the coin can be showing either heads or tails. In example 9, we look at the experiment where 2 6-sided dice are rolled, and we may be interested in any of the following as random variables, and this is just a list of 3 possibilities. For example, x is if x could be the sum of the numbers showing on the 2 dice, which we've already been talking about, and that would be the list of all values from 2 through 12, and that would be all the integers between 2 and 12 inclusive. The 2 comes from 1 plus 1, and the 12 comes from 6 plus 6, and all the values in between are possible. Another random variable we could define is y equals the difference between the numbers showing on the 2 dice. So here we would take the first die minus the second die. So you'll see here that we can actually have negative values in this particular case, because if the first die has a smaller value, that's what happens. So for example, the most negative value here of -5 results from getting a 1 on the first die and a 6 on the second die. So you get 1 minus 6 is -5. And then if you switch those around, we would get 6 minus 1 gives us +5, which is the highest possible integer value. And we would be able to get all the integer values in between as well. Now, if we define a third random variable here, z equals the product of the numbers showing on the two dice, this one works a little bit differently. The minimum value is 1, which is resulting from 1 times 1, and the maximum value is 36, which is 6 times 6. And then not all integer values in between are possible. The next largest after 1 would be 2, which is either from 1 times 2 or 2 times 1. And then the second largest is 30, which is from 5 times 6 or 6 times 5. But you can see that there are numbers missing between 30 and 36 that are not possible. So for z, they would not take in all the values, all the integer values between 1 and 36 inclusive. Now note that the above list of random variables represents a very partial list of the possible random variables we could define for the experiment of rolling 2 dice. In example 10, if we're observing lightning strikes during a 24-hour period in some particular area, we might be interested in either of the following random variables. The first one, n, is simply equal to the number of lightning strikes during this period. So that would be 0, 1, 2, 3, and so on. A second random variable we can define as t equals the time between 2 consecutive lightning strikes. So in that case, t can be any value from 0, including 0, if 2 lightning strikes occur at the same time, and then on upwards. And we would write it as t is greater or equal to 0 and less than infinity. The less than infinity implying that there's no particular upper limit. Now, notice that both of the random variables defined above are infinite, as they're both unbounded at the upper end. Also, the second random variable, time, t, is an example of a continuous random variable, since time elapses over a continuum of values starting from t equals 0. In general, the number of possible random variables is limited only by our imaginations, and in practical terms, by those aspects of an experiment which are of particular interest or relevance. The probability of an event is a measure of the chance that the event will occur when the experiment is executed. The probability of an event E is denoted by P bracket E. All probabilities fall along a continuum of values ranging from a minimum of 0 to a maximum of 1. In other words, for any event E, the probability of E is greater or equal to 0 and less than or equal to 1. So in general, if the probability of an event E equals 0, then we can say that E is an impossible event. And if the probability of E equals 1, then the event E is a certain event. And so if the probability of an event E is greater than 0 and less than 1, then we can say that the event E is an uncertain event. Now, the above mentioned range from 0 to 1 represents a decimal range of values for probabilities. An equivalent and other common way to represent probabilities is in percentage form, which essentially just has us multiplying the probability in decimal form by 100. So in other words, the probability of any event E is greater or equal to 0% and less than or equal to 100%. Probabilities for events are generally determined in 2 different ways. Empirical probabilities are determined based upon previous observed data, and an assumption is made that prior relative frequencies of events can be extrapolated into the future. In example 11, A is defined as the event that it rains on the day of the summer solstice. And if the historical record shows that it has rained on 38 out of 50 recorded years on the summer solstice, then we could say that the probability of event A is approximately equal to 38 over 50, or 19 over 25, which equals 0.76 or 76%. Now note, we use the wavy equal sign here to indicate that the empirical probability is at best only an estimate. When we're using empirical data, we generally don't know the true probability with any certainty. And once again, it's another reminder of the uncertain nature of probability and statistics in general. Theoretical probabilities, on the other hand, are determined based upon mathematical properties related to an experiment, or are simply defined as such based upon logic. In example 12, we have the event B defined as the event that a fair coin is tossed and the side showing is heads. Now, we can invoke the notion of fairness and what that means with regard to a coin, together with the fact that a coin has two sides, to come to the conclusion and state that the probability of event B is simply equal to 1 over 2, or 1/2, which is equal to 0.5 or 50%. The following basic rules for probabilities are based upon set theory concepts discussed previously. First is that the probability of the sample space is occurring is equal to 1. In other words, in any experiment, the outcome must come from within the sample space, since the sample space contains all possible outcomes. On the other extreme, we have the probability of the empty set equals 0. In other words, the empty set has 0 probability in any experiment because there must be some outcome. So the empty set has, and since the empty set has no outcomes at all, it's impossible, so it must have a probability of 0. And thirdly, we have the rule that says that the probability of an event E plus the probability of E complement must equal 1. And this rule basically says that in any experiment, for any defined event, it will either happen or not happen. So with respect to any particular event, there's no third option. So in example 13, we see that if we have an event A such that the probability of A equals 0.64, then the probability of A complement would have to be 1 minus 0.64, which equals 0.36. The following rule in particular follows logically from the rules we looked at previously for sets. The probability of E union F is equal to the probability of E plus the probability of F minus the probability of E intersection F. Now in example 14, we are asked to calculate the probability of drawing an ace card or a diamond card from a standard deck of playing cards. So to answer this question, we can define the event A as the event that an ace is drawn, and the event D as the event that a diamond is drawn. So to answer the question, remember, or is like union. So an ace or a diamond would mean that we're looking for the probability of A union D. And so using the rule above, we would find the probability of A, and we would add to it the probability of D. And since both A and D can happen, and that's in particular if we get the ace of diamonds, we would have to subtract that because we've counted that probability twice. So the answer ends up being 4 out of 52 because there's 4 aces, plus 13 over 52 because there's 13 diamonds. So the probability of A is 4 over 52, 4 out of 52, and the probability of D is 13 out of 52. But since we've counted that ace of diamonds twice, we subtract the probability of getting the ace of diamonds, which is 1 out of 52. So the final answer is 4 plus 13 minus 1 over 52, which is equal to 16 over 52, which simplifies to 4 out of 13, or 4 over 13. And this is a good example of a question where we can leave the answer in fraction form. That's considered to be an exact form of the answer, and that's generally an acceptable way to leave the answer for a probability in simplified fraction form if you have it in fraction form, unless you're specifically asked to express the answer either in rounded form or in decimal form to a certain number of decimal places or the nearest percent or that sort of thing. We can see the solution also in the following Venn diagram, which illustrates it quite nicely. We can see that the set A has a probability of 4 out of 52, which is split into the 3 over 52, which is the non-diamond aces, and then the one ace of diamonds. And similarly, the diamonds are a total of 13 out of 52, which are split into the 12 that are not aces and the one that's an ace, which is again the ace of diamonds. So the first one is the set A, the second one's the set D, and the intersection there is the 1 out of 52, that's the ace of diamonds. And we can see also as well that there's 36 cards that are neither aces nor diamonds. So we could see from the diagram that if we added that up, we would get the 16 out of 52, which equals 4 out of 13. If two events are mutually exclusive, then the probability of their intersection is 0. And therefore, the previous formula reduces to the probability of E union F is equal to simply the sum of the probability of E plus the probability of F. In example 15, we're asked to calculate the probability of drawing a diamond card or a black card from a standard deck of playing cards. So if we define our events as D equals the event of drawing a diamond card and B equals the event of drawing a black card, since diamond cards are all red, it's not possible to draw a card that is diamond and black. In other words, events D and B are mutually exclusive. And so the probability of D intersection B equals 0. So therefore, the probability of getting a diamond or a black card is equal to the probability of getting a diamond plus the probability of getting a black card. And since 13 out of 52, or 1/4 of the deck, is diamonds, that would be 13 over 52, and the probability of getting a black card is half, which is 26 over 52. So that equals 13 over 52 plus 26 over 52, or more simply 1/4 plus a half, which is 1/4 plus 2/4, which is equal to 3/4. And the Venn diagram on the slide shows the probabilities and how they sit given that events D and B are mutually exclusive. When an experiment has outcomes that are equally likely, then the probability of any event, which is a subset of these outcomes, is simply equal to the proportion of the sample space comprised of these outcomes. In other words, the probability of event E equals the number of elements in E, or the number of outcomes in event E, divided by the number of elements or outcomes in the sample space. In example 16, we look at the situation where two fair dice are rolled, and we're asked to calculate the probability in A that both dice show the same number, and in B, the probability that the sum of the numbers showing equals 10. So to answer these questions, we start by looking at the fact that if we roll two dice, the number of elements in the sample space is equal to 6 outcomes for the first die times 6 outcomes for the second die, which equals 6 squared, or 36. And so our sample space consists of the 36 outcomes going from 1 and 1 to 1 and 2, etc., all the way up to 6 and 6. Now, if both of these dice are fair, then each of the 36 outcomes in the sample space are equally likely. And so therefore, we can say that the probability of any event that we define, E, would equal the number of outcomes in E divided by the number of outcomes in S. And that will be true for any event E made up of any subset of the sample space S. So in part A, if we define A as the event that both dice show the same number, we can see then that the elements of A are all the possibilities 1 and 1, 2 and 2, etc., all the way through 6 and 6. And clearly we can see that there are 6 such outcomes. So the probability of this event is equal to the number of elements in the event A, which is 6, divided by the total number of elements in the sample space, or the total number of outcomes in event A, which is 6, divided by the total number of outcomes in the sample space, which is 36, which reduces to 1 over 6, or 1/6. In part B, we can define the event B as the event that the sum of the two dice equals 10. Now, if we list the events, the outcomes that produce that sum, we can see that that is limited to just 3 outcomes, 4 and 6, 5 and 5, and 6 and 4. So the number of elements or outcomes there is 3. And therefore the probability of event B equals 3 over 36, which equals 1 over 12. In example 17, a fair coin is tossed and then a fair die is rolled, and we're asked to calculate the following probabilities. In part A, we're asked to find the probability of event A, which is the event that the coin shows heads. In part B, we're asked to find the probability of event B, which is the event that the die shows a 1. And in part C, we're asked to find the probability of the intersection of those two events. So to answer this question, we start off using the premise that the coin and the die are fair, which would make each of the overall outcomes equally likely, and we can list those outcomes as being everything from heads 1 through heads 2 all the way through tails 5 and tails 6. So using the multiplication principle, we can determine that the number of outcomes in the sample space is equal to 2 times 6, which equals 12. So to answer part A, the event A is that the coin shows heads, so the list of possible outcomes there would be heads 1, heads 2, all the way through heads 6, and that the number of outcomes there is equal to 6. So the probability of event A equals 6 over 12, which reduces to 1/2. And in B, the event B is that the die shows a 1, which we can list as the outcomes including heads 1 and tails 1, which is just 2 outcomes. So the probability of B equals 2 over 12, which simplifies to 1 over 6. And finally, to get the probability of A intersection B, we're looking for the probability of the event that both the coin shows heads and the die shows a 1. And of course, that can only happen one way, which is if you get heads and then a 1. So the number of outcomes for that event is 1, and so the probability of A intersection B equals 1 over 12. In example 18, we toss a fair coin 3 times, and this time we're asked to calculate the following probabilities. In part A, we're looking for the probability of event A, which is the event that the first coin toss is heads. In B, we're looking for the probability of event B, which is the event that exactly 2 heads are obtained. And in part C, we're asked to find the probability of the intersection of events A and B. So we begin our solution the same way, with the premise that since this is a fair coin, all of the outcomes in the sample space are equally likely, and there are 2 to the power 3 equals 8 of those that you see listed on the slide. Event A is the event that the first coin toss is heads. So one way of counting the number of outcomes in event A is to consider that there's only one possible outcome for the first toss, which is that it must be heads, and the other 2 tosses can come up either heads or tails. So we get 1 times 2 times 2, or 1 times 2 squared equals 4. And you can see those possibilities listed on the slide. And so the probability of event A is equal to 4 over 8, or 1/2. Now, part B asks for the event that exactly 2 heads are obtained. Now, there's a number of ways of working this one out. One way is to just list the possibilities. Another way is to think about it this way: if there's 3 tosses and 2 heads, then we have a total of 3 positions in which to choose from to put 2 of them as heads. So we can think of one way of calculating this is to use the calculation 3 choose 2, which works out to be 3. And you can see that heads, heads, tail, head, and tail, head are the only ways of getting exactly 2 heads. So the probability of event B equals 3 over 8. Now, to figure out the intersection of events A and B, we're considering all of the outcomes where the first coin toss is heads and there's exactly a total of 2 heads out of 3. So, one way of looking at this is to simply start with the list of possible outcomes in part B and just look for the ones where heads, the first outcome is, the first coin toss results in heads, and you can see that the first 2 in the list meet that criteria. So those 2 outcomes would comprise A intersection B. So the number of outcomes in A intersection B equals 2. So the probability of A intersection B equals 2 over 8, or 1/4. If we look back at the results of the previous 2 examples, we can see an important distinction between them. In example 17, we got probability of A equals 1/2 and probability of B equals 1/6, and the probability of A intersection B equals 1/12. Notice that in this case, the probability of the intersection of A and B equals the probability of A times the probability of B. In other words, equals 1/2 times, in other words, 1/2 times 1/6 equals 1/12. In example 18, on the other hand, we get probability of A equals 1/2 and probability of B equals 3/8, and the probability of A intersection B equals 1/4. And in this particular case, 1/2 times 3/8 does not equal 1/4. In fact, it equals 3 over 16. So in this case, the probability of the intersection of A and B does not equal to the product of the probabilities of A and probability of B. Now, the reason for this difference is that in example 17, events A and B, and event A is that the coin is heads, and event B that the die equals 1, are events that are independent of each other, which means that their probability of intersection simply equals the product of the 2 separate events' individual probabilities. In example 18, meanwhile, event A is the first coin toss is heads, and B, which is that we get exactly 2 heads, those are dependent upon each other, meaning that their probability of intersection is not simply equal to the product of the 2 separate events' individual probabilities. Unlike in the previous example, 17, where the results of a coin toss and a die roll should have no influence upon each other, it should not be difficult to see how the event of getting 2 heads out of 3, which is event B, would be influenced by whether or not the first coin toss is heads, which is event A. Indeed, event B becomes more likely if event A occurs and less likely if it doesn't. In general, if 2 events A and B are independent, then the probability of their intersection equals the product of their individual probabilities. The above rule can be used to test whether or not events are dependent upon each other, as we have previously done with the events of examples 17 and 18. A further generalization of the above rule can be stated as follows. If n events, E1, E2, all the way up to En, are all mutually independent of each other, then the probability of the intersection of all these events is simply equal to the product of the individual probabilities of each event. In example 19, we have the probability of event A equaling 0.3 and the probability of event B equaling 0.45 and the probability of event C equaling 0.2. Now, if events A, B, and C are all mutually independent of each other, therefore the probability that A, B, and C all happen, in other words, the probability of A intersection B intersection B intersection C, would equal 0.3 times 0.45 times 0.2, which equals 0.027. One last note about independence versus dependence. From the rule for independence that probability of A intersection B equals the probability of A times the probability of B, we can conclude that mutually exclusive events where the probability is not equal to 0 must always be dependent, because for such events, first of all, If the probabilities aren't equal to 0, then the product of the two probabilities will never equal 0, and that's just basic mathematics. And meanwhile, if, as per the definition of mutual exclusivity, if two events A and B are mutually exclusive, then the probability of their intersection will actually equal 0 because there is no intersection between mutually exclusive events. On the other hand, events that are not mutually exclusive, well, they have an intersection with the probability not equal to 0. And in the case of non-mutually exclusive events, the events may actually be either independent or dependent. And the overall situation can probably best be summed up via the diagrams that you see below. Now, in the diagram on the left, we have two events that are mutually exclusive. Now, mutually exclusive events are always dependent, and that may seem like a bit of a misconception. Or that happens to be a kind of a common misconception, because in fact, based on the way in the English language the use of the words independent or dependent in a non-mathematical sense, if you look at those two circles in the Venn diagram on the left, you might think of those two sets or circles as being independent of each other. But in the mathematical sense, in a probability sense, what's really happening is that if you are in one of those sets, that precludes the other set from happening. So that's actually the most extreme form of dependence. So when we have mutually exclusive events, they are always dependent. On the other hand, if events aren't mutually exclusive, in other words, if there is an intersection like we see in the diagram on the right, then those events can turn out to be either independent or dependent. And in fact, the way that we determine which one it is mathematically by testing to see whether the value of the probability of the intersection is exactly equal to the product of the individual probabilities of the two sets. If they are equal, then we say that the events are independent, whereas if the probability of the intersection does not equal to the product of the individual probabilities, then we would conclude that the events, while being not mutually exclusive, are still dependent events. Probability problems are diverse in both type and level of difficulty. In many situations, however, the application of counting principles can reduce a problem down to a workable form. The examples which follow illustrate how we can invoke these counting principles to answer challenging problems. In example 20, a 4-card poker hand is drawn randomly from a standard deck of playing cards. And we're asked to calculate in part A the probability that all 4 cards are of different suits, and in part B, the probability that at least one card is a club. So, to answer these problems, to answer these questions in part A, we start with part A. Now in part A, we can start with looking at the overall sample space, and that will apply to both parts A and B. So the total number of 4-card poker hands, which comprises our sample space, is simply equal to the number of ways of choosing 4 cards from a deck of 52. So that just equals 52 choose 4. Now that's a large number, and it actually works out to be 270,725. So you can see that the notation 52 choose 4 is good to use, and it makes things pretty clear as we go. Now, let's define the event A as equaling the event that all 4 cards are of different suits. Now, clearly, for this to happen, in the diagram you see below shows how we can figure out the number of ways of calculating the number of outcomes in event A. So in order to get 1 card from each suit, we would be choosing exactly 1 out of the 13 for each of the 4 suits. So what we would be doing is that we would be doing 13 choose 1, because there's 13 in each suit, and we would be choosing 1 of them. And we would do this 4 consecutive times, once for each suit. So the number of outcomes in event A is 13 choose 1 to the power of 4, which is equal to 13 to the power of 4. And that gives us the number 28,561. And since each poker hand is equally likely, therefore the probability of A, we can use the rule for equally likely events. And so the probability of A just equals the number of ways that A can happen over the total number of outcomes in the sample space, which equals 13 choose 1 to the power of 4, divided by 52 choose 4, which gives us 28,561 divided by 270,725, which rounds to the nearest percent, which rounds to 0.11, which also equals 11%. So note that either of the three ways of presenting this answer are acceptable because they all illustrate clear ways of explaining how this probability is determined. Note that we just solved part A using combinations, which is logical in the sense that order doesn't matter in a poker hand, only the combination of cards that are drawn. In other words, it doesn't matter how you hold them in your hand. A poker hand that you have in your hand is a poker hand no matter what the order is in the way you hold those cards. It is possible, though, to approach this problem from a very different angle, where we look at the selection of the hand as an ordered sequence of tasks. So the diagram that you see on the slide below shows the 4 cards as 4 boxes. And to figure out the probability of event A, we can think of it in the following way. First of all, we can think about the first card can be any card. So one way of looking at this is we could pick any card from the deck and we still have the possibility of getting 4 different suits. There's no restriction on the first selection or the first card. However, once you've chosen that first card, for the second card, we know there's 51 cards. And that's why, by the way, in the first box, we would put 52 out of 52 or 52 over 52, which really just equals 1. But we leave it as 52 over 52 just to illustrate and point out that all 52 of the 52 cards are available to be chosen in order for us to have this sort of hand. So the second card, on the other hand, now that we've taken one card out, there's 51 cards left, so the denominator is 51. But since we've chosen one suit already, we don't want any more cards from that suit. So the other 12 cards from that suit we chose in the first card is no longer available in order for us to still be able to have this hand, in order for us to still have 4 different suits, in other words, in order for event A to happen. What we are allowed to have for the second card is any of the other 3 suits, which is 3 times 13, so the other 39 cards out of 51. And then we use the same logic for the other 2 remaining cards. For the third card, there's a total of 50 cards left in the deck after we've chosen 2, but only 2 suits, the 2 suits that we haven't chosen, are still eligible, and that's 2 times 13, which is 26. And so the probability for the third card is 26 out of 50. And then for the last card, we can only pick the last suit that hasn't been chosen yet. So out of the 49 remaining cards, only the 13 in the last suit is a possibility in order for event A to happen. So the answer ends up being the product of those 4 probabilities, which ends up working out to give us the same answer that we got doing it the first way, and that rounds to approximately 0.11. So we get the same answer as before, and this is an example of how a probability can be solved in different ways. And this is a very common theme in probability, actually. Now, it's recommended that you choose an approach that works best for you. In other words, that generally means choosing the method whereby you can best see the underlying problem for yourself and therefore work towards getting the correct answer. Now, in part B, we're looking for the probability. We can define the event B as the event that there's at least one card in the hand is a club. So the probability of event B can be rewritten as the probability of getting greater than or equal to 1 club in the hand, and we just use that short form there. And that can happen as either having 1 or 2 or 3 or 4 clubs, and there's 4 different scenarios there, and that can get quite complicated to work out. So the easiest way to do that would be, as we've done before, is to use this concept of the complement. So it's much quicker to just figure out the probability of getting no clubs and just subtracting that from 1. And that would give us the probability of the complement of getting no clubs, which is actually the event B, which is the event of getting at least 1 club. Now the probability of getting 0 clubs is done as follows. The denominator is the same. It's the 52 choose 4. That's our sample space. Now to get 0 clubs, what would happen there is, if we can sort of partition the deck into 2 groups. One is the group of 13 clubs, of which we're picking none, and then the 39 other cards, which are from the other 3 suits, of which we have to pick all 4. So we get 13 choose 0 times 39 choose 4 divided by 52 choose 4. Notice that the 13 and the 39 on top add up to the 52, and the 0 and the 4 on top add up to the 4 on the bottom. So what we end up with is 1 minus 82,251 over 270,275, and that works out rounded to the nearest percent as 0.70 or 70%. In example 21, a fair coin is tossed until a tail is obtained, and we're asked to calculate the probability that the coin will be tossed at least 3 times. So to answer this problem, what we can do is we can first we can define the event A, which is the event that the coin will be tossed at least 3 times. Now, what we can further do is we can define a random variable. Let's call it x, and let's define x as the number of tosses required to get that tail. So by logic, the possible values of x would be 1 if you get tails the first time, and then 2 if it takes you to the second time, and then 3 and so on. And if you think about it, theoretically there'd be no upper limit on this if you kept getting heads. So it's an infinite set of values. It's unbounded at the upper end. So that's going to pose a bit of a challenge for us, but and we'll deal with that in a moment. But we can restate the question that we're trying to find. The answer that we're trying to get is the probability of event A, which is the probability that x is greater or equal to 3. Now that equals the probability that x equals 3 plus the probability that x equals 4 plus the probability that x equals 5, and so on without end. And this is a problem because it's an infinite number, an infinite sum of terms. And in order to be able to do this without having to count to do an infinite number of calculations, it's obviously much easier. In fact, it becomes feasible by necessity to invoke the complementary principle of probability here, which is that the probability of A can be worked out as 1 minus the probability of A complement. And A complement is the probability that x is less than 3, which is just the probability that x equals 1 or 2. And that is a finite number of calculations. That's just 2 calculations that we need to do. So that's the way we proceed. And the diagram on the slide illustrates just how straightforward it is to calculate these individual probabilities. We use the boxes here for simplicity's sake. And so the probability that x equals 1 is just the probability of getting tails on one toss of the coin, and obviously for a fair coin that'll be just 1/2. And the probability that x equals 2, that would imply, now this experiment always ends with a tail. So if x equals 2, it must mean that we got heads and then tails. And since the probability of both heads and tails are 1/2 for both, the answer to this question, for x equals 2, is just 1/2 times 1/2, or 1/2 squared. So what we end up with is that the answer to this question is equal to 1 minus the sum of 1/2 plus 1/4. And that gives us 1 minus 3/4 for a final answer of 1/4. The following is a set of practice questions meant to provide a review of the material covered in this lesson. Question 1. Events A and B are mutually exclusive with probability of A equal to 0.3 and probability of B equal to 0.4, and we're asked to calculate the following. For part A, the probability of A union B. For part B, the probability of A intersect B. For part C, the probability of A complement intersect B complement. And for part D, the probability of A complement union B complement. So to answer these questions, a good place to start is by constructing a Venn diagram. Now, events A and B are mutually exclusive, so we model this by drawing the box for the universal set, and inside we draw two separate circles with no intersection. So we keep in mind here that because the events are mutually exclusive, they don't overlap, they don't intersect, and therefore the probability of intersection for A and B is equal to 0. So for part A, since the events are mutually exclusive and there is no intersection, the probability of A union B will simply equal the probability of A plus the probability of B, which equals 0.3 plus 0.4, which equals 0.7. For part B, as we just mentioned a moment ago, since the events A and B are mutually exclusive, the probability of the intersection of them is equal to 0. For part C, the most efficient way to answer this question of finding the probability of A complement intersect B complement is to remember that in a Venn diagram such as this, every distinct region is an intersection between one set or its complement and the other set or its complement. So in this case, we have A complement intersect B complement, which means we're not in A and not in B, which must be the region outside of the two circles, which equals 0.3. And finally, for part D, here we have a union, which doesn't work as easily. So this is not just a simple matter of looking for one of the distinct regions in the Venn diagram. We have A complement union B complement. So one valuable approach here is to use the idea of the complement, which are the rules where if you apply a complement to a set of brackets, that it makes all of the pieces inside opposite. So if we look at A complement union B complement and take the opposite of all of those, which is A intersect B, then we're looking for the probability of the complement of A intersect B. And the probability of that would equal 1 minus the probability of A intersect B, which, as previously discussed, that is, the intersection is 0. So the answer here is equal to 1 minus 0, which equals 1. Question 2. The following information is given about events A and B. First, the probability of A intersect B complement equals 0.45. Next, the probability of the complement of A union B is equal to 0.3. And finally, the probability of A complement equals 0.4. Based on this information, we're asked to determine whether A and B are independent or dependent with respect to each other. So as with the previous question, a Venn diagram is a natural starting point to help us to be able to answer this question efficiently. So what we see in the slide here is each of the given information analyzed and turned into information that we can then put into the Venn diagram. So we start by setting up our Venn diagram. Now we don't know here whether or not the two events are independent or dependent. In fact, that is our task here. So we make the assumption that the two sets can possibly have an intersection, that they may or possibly overlap. So we draw two circles that overlap with an intersection, and we label them A and B. Now, it's still at this point possible, generally speaking, before we've fully analyzed the situation, that the probability of that intersection region could be 0, which would actually then mean that the two sets were mutually exclusive. But now we're going to analyze the information that's given to determine all that. So we start with the first piece of information that says that the probability of A intersection B complement equals 0.45. And this is a good starting point because recall from the previous question that when you are given an intersection of sets for a Venn diagram, that gives you one of the distinct regions in the Venn diagram. So A intersect B complement means in A and not in B. So that is the left region of the A circle, the crescent shape, and that equals 0.45. So we put 0.45 in there. Now, the next thing we can do is if we look at the probability of A union B, or the complement of A union B. Now again, unions are a little trickier because they don't represent distinct regions in a Venn diagram like this. However, we have a complement here. So applying the complement rule, the complement to a set of brackets rule, we end up with the complement of A union B equaling A complement intersect B complement. So what we're looking for here is the distinct region where we're not in A and not in B, which is the outside of the two circles. So we put 0.3 into that region. Next, so at this point, the regions that we don't have values for, there are two remaining regions. Now, once we can get down to, there's 4 distinct regions overall, and we've got 2 of them right now. We have values for 2 of them. Once we get 3, then we can just subtract the sum of those 3 from 1 to get the last one. So we really need to figure out one more. So an approach that we can take here is we know that the probability of A complement is equal to 0.4. So we simply use the rule that the probability of A must be 1 minus that, or 1 minus 0.4, which equals 0.6. So now we know that the total of the 2 distinct regions that make up the set A must equal 0.6, and since the part of A that's not in B is 0.45, we simply subtract 0.45 from 0.6. So we get that middle area, the intersection of A and B. So the probability of A intersect B is equal, therefore, to 0.15, and we put that in that middle piece. Now the last remaining distinct region is the probability of A complement intersect B, which must just equal to 1 minus 0.45 and 0.15 and 0.3, which equals 1 minus 0.9, which equals 0.1. So now we have a complete Venn diagram. So from that, we can do the test of independence. And recall that if 2 events are independent of each other, so if A and B are independent of each other, then the probability of A intersect B must equal the probability of A times the probability of B. So we test that. So on the left side, the probability of A intersect B, that's that middle overlapping area, and which we now know is 0.15. And the probability of A, we just worked out a few moments ago, is 0.6. And we times that by the probability of B, which is the sum of the intersection of A and B and the intersection of A complement in B, which is 0.15 and 0.1, which is 0.25. So 0.6 times 0.25 is our right side, which does work out to be 0.15. So we confirm that the probability of A intersect B does in fact equal the probability of A times the probability of B. Therefore, A and B are independent of each other. Question 3. A 5-card poker hand is drawn from a standard deck. Calculate the probability that A, the hand contains exactly 3 aces, B, the hand contains at least 2 hearts, C, the 4th card drawn is the 7 of spades, and D, the hand contains more red cards than black cards. For part A, we're looking for the probability of exactly 3 aces. So to do this, we can conceptually divide the deck into two parts. There's a set of 4 aces and a set of 48 non-aces. So to get exactly 3 aces, now the sample space will be the number of ways of picking 5 cards from 52, which is the number of cards in a standard deck. So our denominator is 52, choose 5. And our numerator would be 3 aces from 4, so 4, choose 3, times the remaining 2 cards must come from the other 48. So that's 48, choose 2. So the answer then becomes 4, choose 3 times 48, choose 2 over 52, choose 5, which equals 4,512 over 2,598,960, which rounds to 0.0017 or approximately 0.17%. For part B, the probability of getting at least 2 hearts, the way we start with this one is at least 2 hearts can be anywhere from 2 to 3 to 4 up to 5 hearts out of 5 cards. So there's 4 scenarios we would need to work out separately. On the other hand, the opposite of at least 2 hearts, or the complement of that, is just 0 or 1 heart. So that's just 2 separate calculations to make. So it's quicker in this case to use the complement rule where we work out the probability of the complement and subtract it from 1, which is what we do. So to get the probability of 0 or 1 heart, we just add the 2 separate scenarios. And as we see in the slide, each scenario, the probability has a denominator of that 52, choose 5. And the numerators are respectively for no hearts, it would be, oh, and we have to again, divide the deck of cards now into the relevant set. So in this case, we're looking at hearts versus non-hearts. So there are 13 hearts. So we're looking at 2 sets, a set of 13 hearts and then the remaining 39 non-hearts. So for no hearts, it would be 13, choose 0 times 39, choose 5 over 52, choose 5. And then plus, for 1 heart, it would be 13, choose 1 times 39, choose 4 over 52, choose 5. So 1 minus the sum of those equals 1 minus 1,645,020 over 2,598,960, which equals 953,940 over 2,598,960, which rounds to 0.37 or 37%. For part C, now, while parts A and B involve fairly complex counting theory, this particular question is actually best answered by a more simple, straightforward, logical thinking approach. Each of the 52 cards in the deck has an equal chance of being selected in any of the 5 cards drawn. In other words, there's a kind of independence of probability, not in the sense that what happens on each draw is independent of what comes next, or vice versa, because there is a dependency. In other words, the probability of what you get in a subsequent draw of the card does indeed depend on what has already been taken out of the deck. But what's the important point here is that if you're going to get the 7 of spades or any other particular card in this hand, it's just as likely to be in the 4th card as it is in the 1st, 2nd, 3rd, or 5th cards in the hand. And we use this idea here. So the idea really that we can then focus on is we just need to think of this as being nothing more than drawing 1 card out of the deck. So the answer to this question is just there's only 1 7 of spades out of a total of 52 cards. So the answer equals 1 over 52. Now, for part D, we can approach this problem in a similar way to part C by using logic rather than just a simple formula that we've used, one of the sort of basic formulas for probability. Otherwise, as with part C, this can get rather complicated. And we're looking for an efficient, elegant way of answering each of these questions. In this case, we're interested in the probability that the hand contains more red cards than black cards. Now, there's a lot of different ways that you could get more red cards and black. Well, getting more red cards and black cards could be that you get 3 red versus 2 black, or 4 red versus 1 black, or all 5 red versus no black. So there's actually 3 scenarios there we would need to work out separately. However, it would be much simpler to start by realizing or focusing on the fact that there's an odd number of cards in these poker hands. This is a 5-card poker hand. So any hand must either have more red cards or more black cards. In other words, it's impossible to get an equal number of red and black cards simply because there's an odd number of cards. Now, since the number of red and black cards is equal, it must be true, therefore, that the probability of getting more red cards would have to be exactly equal to the probability of getting more black cards. And those are the only 2 colors of cards. So the answer to this question must simply be 1/2. Question 4. A fair coin is tossed until 2 heads are obtained. And we're asked to calculate the probability that A, the minimum number of tosses is required, and in part B, that 6 tosses are required. So we know that with this experiment, this experiment must end with the second head obtained. In other words, we'll toss the coin until we get the second head. And what that means is that the tosses before that last toss, which will certainly be a head, all the tosses before that one will have to have only 1 head, exactly 1 head, no more, no less, with the rest, if there are any, being tails. So let's start by defining a random variable, x, which equals the number of tosses required. Now for part A, we're asked to find the probability of getting the minimum number of tosses. Now we first need to figure out what that is. Well, if we toss the coin until we get 2 heads, then the minimum number of tosses must be 2, and that is the case where we get heads and then heads. So twice in a row we get heads on the first 2 tosses. And so the probability of doing that can be modeled simply by drawing a box for each of those 2 tosses. We label them showing that we're getting heads, and if this is a fair coin, the probability of getting heads is 1/2. So the answer to this question is simply 1/2 times 1/2, or 1/2 squared, which equals 1/4. For part B, we're asked to find the probability that 6 tosses are required. Now this is more complicated because there are many more ways than this can happen. In part A, there was really only one sequence that we could get to get the minimum number of tosses. The first toss had to be heads, the second toss had to be heads. This time, we're talking about 6 tosses, exactly 6 tosses, of which 2 are heads, and therefore 4 are tails. Now, there's a lot of variation possible in terms of what some of these tosses are, in terms of whether they can be heads or tails. In fact, the only one of the 6 total tosses that has to go in one certain way is that last toss, because as discussed previously in this solution, we end the experiment with a head. So the diagram here shows the way to logic this out. We draw 6 boxes, and we make a note of the fact that the last toss on the far right is definitely heads. And we put the probability 1/2 in there. Now note, of course, that whether any toss is heads or tails, the probability is going to be 1/2 because it's a fair coin. So all of the boxes are going to contain 1/2. So part of the answer is just that we get 1/2 to the power of 6. However, there's more work that needs to be done. And where that comes from is the fact that while that last toss must be heads, the first 5 tosses actually can be a multitude of different possible arrangements. as long as they contain the one other head and the 4 tails. So we need to figure out the number of ways of arranging that. And as it turns out, we can think of this like a string, like a word made up of 1 H and 4 T's. And we know the rule for that. That's the total number of objects, which is, or total number of coin tosses, which is 5 factorial, divided by 1 factorial for the one head and 4 factorial for the 4 tails. So the final answer to this question is, and we also notice that from our previous discussion, we could call this 5 factorial over 1 factorial, 4 factorial, or even just simply 5 factorial over 4 factorial. But recall that since on the bottom, the numbers 1 and 4 add up to 5. In other words, there's 2 types of letters or 2 types of results, the heads and tails. So this fits the formula for a combination. So we can call this 5 choose 1. We could also call it 5 choose 4. And the one that we're choosing here is simply the position to put the 1 heads is one way of thinking of it. Or if we called it 5 choose 4, which we could, that would be the number of ways of deciding where the 4 tails go. So we'll go with 5 choose 1. So the final expression for this answer is 5 choose 1 times 1/2 to the power 6, which works out to be 5 over 64, which rounds to 0.078 or 7.8%. Question 5. What is the probability that among a group of 30 students, there are at least 2 people who share a common birthday? And we can assume for this problem that none of the students are born on a leap day, i.e. February 29th, which only occurs once every 4 years. And we can assume that all of the other birthdays or all the other days of the year are equally likely. This actually happens to be what's commonly known as the classic birthday problem. Now, this is a fairly complicated problem to work through, but complicated problems, as we've already seen, are if they're approached with a view to logic and a focus on finding an efficient, elegant way of solving it, can yield a fairly straightforward, easy to understand solution. And that's going to be our goal here. Now, the event that there is at least one common birthday among the 30 people has many different ways of occurring. So for example, we could have just 2 people out of the 30 sharing a birthday and no other common birthdays. Or we could have 2 pairs of people with a common birthday. Or we could have 3 people with 1 common birthday. Or we could have 2 people with 1 common birthday and 3 with another, etc., etc. And as it turns out, with a total of 30 people, there's quite a very unworkably almost large, in realistic terms or in a practical sense, a very, very difficult number of different scenarios that we would need to consider separately. So that would become a problem of sort of astronomically large scale of difficulty. So what we're trying to do is look for a key principle or idea that will allow us to solve this problem much more elegantly. And it turns out that we can invoke the complementary principle again, as we've done previously. In other words, the key idea here is that at least one common birthday among the group is simply the opposite of there being no common birthdays. So in other words, the answer to the question of the probability of at least one common birthday is simply going to be 1 minus the probability of there being all different birthdays. So what we're really going to go after here mathematically is to figure out what is that probability that all the birthdays are different, focus on that, and once we get that, we just subtract the answer from 1. So how do we do this? Well, say we arrange the 30 people. So this is just a matter of drawing 30 boxes. Now we don't need to draw the 30 boxes as you can see on in the diagram on the slide. we can just start by drawing a few. We draw the first 3, and then we have the sort of dot, 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 and the last 2. And that should be sufficient to illustrate what's happening and provide us with a means of finding whatever pattern or patterns there are. And then we proceed as follows. We start with the first person. Now, what we're trying to do is we're trying to figure out how many of the total of 365 days the first person can have as their birthday. And of course, since they're the first person that we're looking at, there's no other birthday that's yet been selected. So all of them are possible to choose. So we put in 365 divided by 365, 365 over 365. And then we move on to the next person, the second person. And this is actually this should seem fairly straightforward and logical. For the second person, we have used up one of the birthdays. So out of 365 birthdays, we can use any of the remaining 364. And then for the next person, that number reduces by 1 again to 363, and so on, all the way down. So when we get to the 30th person, we've used 29 before we get to them. So we simply minus 29 from 365. So we can see the last two are 336 and 337 and 336. And then the question is, well, what is the pattern or patterns that we're getting in these boxes? Well, it's clear to see that each of the 30 boxes has the same denominator of 365. So those boxes, and of course we're using the multiplication principle because this is a sequence that of birthday allocations. So we have 365 to the power of 30 as our denominator. And on the top, we're multiplying down from 365 30 consecutive times, which, as we've discussed previously in the lesson on permutations, is 365 permute 30, 365p30. So the answer to this problem is that the probability of there being at least one common birthday is equal to 1 minus 365p30 over 365 to the power of 30, which rounds to 1 minus 0.29, which rounds to 0.71 or 71%. I hope that you found this video helpful. If you liked it and would like to see more from Ursa Campus, then please subscribe. And also, if you'd like to send your feedback, that's always welcome too. Thanks for watching, and I wish you well with your studies.